Buenos días a todos, bienvenidos y bienvenidas a esta última charla de este año de colaboración entre Sociedad Astronómica Dominicana y la Oficina de Divulgación Astronómica de la Unión Astronómica Internacional para el Desarrollo. Este día tenemos el honor de recibir a un profesor de física y astronomía de la Universidad de Oslo, el doctor David Mota, quien nos estará hablando de una charla con respecto a materia oscura, y vamos a tener la oportunidad de hacerle preguntas al final, aunque él dice, y doy la autorización porque así lo ha hecho, que pueden interrumpirlo en cualquier momento para realizar alguna de las preguntas. La Unión Astronómica Internacional y Sociedad Astronómica Dominicana son instituciones de divulgación científica sin fines de lucro que tienen como meta la divulgación de la ciencia y la apropiación social de esta disciplina a través de la astronomía. Nos enorgullece mucho hoy tener a una persona de tan alto currículum académico y de tanto tiempo al servicio de la educación científica en su país y en la Universidad de Oslo. Welcome, Mr. David Mota. I have already introduced you. It's a pleasure for us to have you here today, and we hope this will be the first one of many more to come. Tonight for you, today for us, we will doing this talk about the subject that you will start sharing your screen now, and I will now let you all the things about this event on your hands. Enjoy. You could feel free yourself, because we are really happy for you to have you here, and the students here will be also writing down their questions and making your question as the progress of the talk or at the end.
Very good. Yes, thank you very much. It's indeed a pleasure to be here. I will talk about some research, like recent research that has been done worldwide. And this is, in fact, a research based on a very pertinent question that scientists all around the world have been asking the questions. You know, it's about dark matter, gravity beyond general relativity. And I will explain you, hopefully in an understandable way, what I mean by dark matter and what I mean by gravity beyond general relativity. So please feel free to interrupt me during my talk. It's not a problem if you don't understand something. So because I don't know what is the level of physics that you know, even for astronomers, and I think this is important for the students, there are never stupid questions, you know, just ask them. If you don't know something and you don't understand, please feel free, just interrupt, ask the question. You know, this is that's the most important, because I'm here for you, you know, to try to teach you something, to convey some message from what has been done in astronomy and cosmology in the last 10 to 20 years. Okay, so I will start then my talk.
Professor, sorry, before you start, I will ask to all the attendants to make sure that their mics are turned off meanwhile you are giving on your presentations. If you have one question, then open your mic, and do the question. Now we will start.
Yes, very good, thank you. Okay, so scientists, and in particular physicists and astronomers and cosmologists, we'd like to describe the universe as we see it, and the laws, the physical laws that basically all the matter in the universe follows. So, and for that, physicists, we have built up what I call two pillars in physics to describe our universe and everything that's in there. So one of the most important things that there is in the universe that we need to be able to describe is matter, because we know, we look around us, we are made of matter. You are sitting in front of a laptop, there's matter in front of you, there's the Earth, there's stars, there's galaxies. So matter exists in the universe. So if we physicists would like to describe the universe, one of the first things we need to do is to come up with mathematical equations to describe matter in the universe. And physicists, they were very successful in doing that. So they are able to describe matter by setting up the so-called standard model of particle physics. So the standard model of particle physics is a model for all the particles that we know to exist in the universe. And we have equations for that. We have mathematical equations for that. And this standard model of particle physics basically tells that everything that you see around you, from your laptop, from yourself, to the stars, to the galaxies in our universe, is made of the particles that I'm showing here. So it's made of quarks, and in particular, everything that you see around you is basically made of the up quark and the down quark. There are other quarks in the universe. There are the 4 other ones, which you don't interact with it on your daily life. You don't really see them. We only see them in particle physics accelerators, but we know they exist. Besides that, we have electrons that you are made of. And again, that's basically the 2 quarks here, the up and down quark and the electrons. This is the type of matter that you basically are made of and you see around you, from laptops to stars to planets, etc. But there are other particles. You have neutrinos, and you have also the Higgs boson, which was discovered not so long ago in particle physics accelerators. And you have the forces of nature, which basically connect all these particles together. So you have the electromagnetic force, you have the strong force, you have the weak force, etc. So this is one of the main pillars in physics. So if you want to describe our universe, and we want to describe the matter that exists in our universe, physicists, we use this theoretical model, this mathematical and physical model. Now, this is not enough to describe our universe. We need something else. And the something else that we need after, on top of this, is the fact that matter lives in the universe in a given region of space, in a given region, in a given moment of time. So we need to be able to describe also what is space and what is time in order to describe our universe. And for that, we also have a mathematical formalism that is called nowadays general relativity. This was proposed by Albert Einstein in the beginning of the 20th century. And basically, general relativity is a set of mathematical equations, again, the mathematical formulas, which describe space and time. So space and time, for Einstein, general relativity, this is not a constant thing. These are not absolute quantities that exist in our universe. These are quantities which can change, and basically this change of space and time, these are given by the Einstein field equations. So these are the 2 main pillars in physics, the whole matter that exists in the universe, plus where this matter lives and at what moment in the universe this matter lives. So when physicists put together these 2 theoretical models, this mathematical formalism, they are unfortunately not able to describe everything that we observe, especially at astrophysical and cosmological scales. So this is really strange because with these 2 theories, with the general relativity and the standard model of particle physics, we can describe all the phenomena that we observe on Earth, in our solar system, for instance. But if we go to scales like astrophysical scales, so scales at galaxy scales, if we go even further to clusters of galaxies, and even further in our universe, then we start to have problems. So we cannot understand what we really see. And by that, I'm just giving you here a very brief example. I will tell you very concretely an example of what we cannot understand. But just to give you a quick example here. So if you try to understand how matter is distributed in our universe, so matter and light, light because we basically see light in our universe. So this is what I'm here on the y-axis here. So if you try to see how matter is distributed in our universe in a scale of time, so in millions of years away from us, like we do all these observations. So these are the data points that you can see here on this plot. So these are these data points. So it's real observations. So the observations of these data points are observations from the light that was created at the time of the Big Bang. For instance, how this light is distributed in our universe. For instance, how galaxies are distributed also in our universe. How many clusters of galaxies exist in our universe. So there will be cluster abundances, etc., etc. If we try to put all the distribution in matter and light in our universe, we can only we cannot describe it with the standard model of particle physics plus general relativity. We need to introduce something else, which I'm going to call it dark matter, okay, in order to be able to understand what we see. Now, that means that there is something wrong with our mathematical formalism, with our physical laws at the moment for our universe. So either there is something else, there is some kind of matter in our universe that we don't know, we can't see it, we cannot describe it mathematically and physically, or the way that Einstein has been describing space and time and general relativity is also not correct. But there must be something wrong here, because we cannot, using these two theories, basically explain what we observe at astrophysical and cosmological scales. So, but let me go back 200 years and try to tell you that, in fact, science has been going like that, in fact, for the last, almost since mankind started doing science, in the sense there's always this relation about observations that we cannot really understand and explain, and for that we need to upgrade our physical model. So, for instance, let me hide this one. So, for instance, in the 1830s, astronomers on the 19th century, they have noticed that when they look at Uranus planets, which is orbiting around the sun, Uranus planet did not really follow the expected Kepler law, Kepler orbit. So that was really strange, because, they look at the several planets, they all follow Kepler's law, but not Uranus. And so some of them, they even start to wonder whether the Newtonian law of gravity, which is basically, the law of the physical model that they use to explain the orbit of planets, whether there was something wrong with it, So Newtonian law of gravity, as you all know, basically tells the force is proportional to the mass and inversely proportional to the square of the distance. So this is something like which basically make people wonder at that time whether is the Newtonian law of gravity wrong? Shall we do something about it? But on the other hand, maybe the Newtonian law of gravity is wrong, but on the other hand, all the other planets in the solar system, they seem to follow Newton's gravity very well. So the law of gravity worked very well for all the other planets, but not for Uranus. So maybe some people start wondering, maybe we are missing some planet in the solar system, and this other planet is disturbing Uranus' orbit. And this is, in fact, what was predicted by Urbain Le Verrier and John Adams, that they basically, they said that, no, Newton's law of gravity works extremely well for all the planets in the solar system, so it should work also for Uranus. The only problem is that we are missing a planet. We are missing some matter, which is distorting the orbit of Uranus. But this other matter, it was even called Neptune, they predicted what was its orbit in order to explain Uranus' anomalous orbit. And what is amazing is that Neptune, well, as you all know, Neptune is the planet which comes after Uranus. So it was discovered in 1846, exactly at the predicted position that Le Verrier and Adams predicted. So in this case, our theory of gravity did not need to be upgraded. Newtonian theory of gravity was perfect, was very nice, but we just hadn't seen yet. So there was this planet, this dark planet. It's not dark, now we can see it. But there was this new planet which basically provided the explanation for a phenomena which before we could not explain. But this is going on, in fact, because in fact, a bit later on that century, in 1859, Le Verrier, so he observed that Mercury's perihelion precession, he measured was about 5,600 arc seconds per century. But when you do the calculations using Newtonian gravity, the value that you should get for Mercury's perihelion precession, so that's the orbit of Mercury is basically shifts as it turns around the sun. So, and the calculated, the computed value should be 5,557 arc seconds per century. So Leverrier, like he said, okay, again, we should trust on Newton's theory of gravity. And what is happening is that there is another planet near the sun, an inner planet near the sun, that should be in a given orbit. Leverrier computed the orbit of this new planet, even gave him a name. He called it Vulcan. And he told astronomers at that epoch, just search for it, look for Vulcan, because you will find it. Just like you found Neptune, now you will find Vulcan. And with that, we can explain. Well, I guess as you all know, there is no such a planet called Vulcan. Astronomers have been looking in the solar system for many decades and centuries and never found this Vulcan planet. And in fact, the explanation for why Mercury's perihelion precession was so large only came on the 20th century. So almost like 100 years or almost 200 years after. And that came when Albert Einstein proposed a new theory for gravity. So he has upgraded Newton's theory of gravity. He proposed general relativity. And within the theory of general relativity, and without the need to include any other planet that we can't see in the solar system, you can basically explain Mercury's perihelion precession. So in this case, it was our theory of gravity that was wrong. We were using the wrong mathematical equation to describe the gravity interaction. So with Einstein was a description of space and time in order to explain a given phenomenon. So, as you can see, this kind of, we as scientists, we are always trying to understand what we observe around us. And often we have to upgrade our theoretical models, our mathematical models. And there's always a question within, especially in astronomy, in cosmology, in physics related to astrophysical and cosmological scales, whether it's the standard model of particle physics that needs to be upgraded or our description of the gravity interaction of space and time. Now, let me now come back to try to give a more specific example of the problem of dark matter in astronomy or in cosmology. So let's go back to the solar system first, and let's look at the behavior of the solar system planets, how the planets move around the sun. Okay, so let's take Newton's theory of gravity, which is pretty much the one that it's general relativity at the solar system scale. So let's say it's correct. Yes. So if we look at the solar system, the sun is a huge star, extremely massive. So most of the mass of the solar system is basically concentrated in the center of the solar system. That's the sun. Yes. So it's something that I guess you all know. And what we know as well is that from gravity laws, the gravity interaction, so the force becomes smaller and smaller as we go to the outskirts of the solar system. So planets like Uranus or Neptune or Pluto, they will feel a weaker acceleration due to the gravity force than, for instance, a planet like Venus or Mars or Mercury, because they are much closer to the sun. So the interaction, the gravity force is much stronger, so they feel stronger accelerations. And what that means is that if we are going to have a plot of how the velocity of the planets are distributed in our solar system, so if here on the y-axis I'm showing what is the velocity of each planet as a function of the distance from the sun, so we have Mercury very close to the sun, moving at almost 50 kilometers per second. Then we have Venus moving at around 35 kilometers per second, and so on. So as we go to Neptune or Pluto, they are moving at velocities of around 8 kilometers per second, 8 kilometers per second. So that's much lower velocities. So if we are going to then to show what is the so-called the solar system rotation curves, so how planets move around the sun, we see that the planets closer to the center of the solar system, they should move much faster than planets that are in the outskirts of the solar system. And that's because basically gravity is weaker in the outskirts of the solar system. Now, in the 1950s, so now about 70 years ago, there was an American astronomer called Vera Rubin. And she decided to also do a similar kind of measurement and observations in galaxies. So Vera Rubin decided to measure the velocity of stars in galaxies and to do the similar kind of, like we have the solar system velocity curves, Vera Rubin decided to also measure what would be the velocity of stars in our galaxy. So you can see here, for instance, like one possible kind of galaxy. So where there's a lot of stars in the center of the galaxy, so in the central bulge of the galaxy, many galaxies, they even have a supermassive black hole in the center. Okay, so there's a lot of mass in the center of galaxies. And as we go to the outskirts of the galaxy, it becomes thinner and thinner. So there's less stars, there's less gas in the galaxies. Okay, so Vera Rubin decides, okay, let's then try to measure what is the velocity of these stars along the galaxies. Okay, and in her opinion, again, looking just at general relativity and Newton's gravity, she was expecting then that the stars that are in the bulge of the galaxy, in the core of the galaxy, they should move really fast. While, for instance, these stars that are in the edge of the galaxy, they should move more slower because gravity is weaker at these distances. Yes. So Vera Rubin in the 1950s, when she decided then to plot, to do a graph of the observations for the velocity of the stars as a function of the orbital radius, she should see that in the core, you should see high velocities, but as we go to the outskirts, the velocity of the star should decrease. Just like the solar system, you know, Neptune should move much slower than Mercury, just like in the solar system. Okay, and that's what she did. So she went to observe and measure velocities of stars in galaxies. And what she found out, something very, very surprising, which is that this is what she found out, this white line. So is that the velocity of stars in a galaxy, they do not decrease as you go to the edge of the galaxies. So what she found out is that stars that are at the edge of the galaxy, so that in principle, they should not feel any acceleration due to gravity. They are still moving very, very fast as galaxies, as stars that are in the inner core of the galaxy, near the supermassive black hole, basically. The velocities are pretty much the same, you know? So this is basically, the white line represents the measured, so the observed velocity curves for the galaxy. So as you can see, it's pretty much flat as you go out, even outside the galaxy, you know? So because astronomers are able to measure, there may be not many stars outside the galaxy, but they are still clouds of hydrogen. So astronomers are able to measure the molecules, the velocity of molecules of hydrogen, even outside the galaxies. And they can see that they move as fast as the molecules of hydrogen in the inner parts of the galaxy. And the predicted curve that we expected was this red line, so that the velocity of the stars and the hydrogen clouds, they should decay as we go outside from the center of the galaxy. Yes. So this was really a huge surprise for the whole astronomy community. So the only way of explaining this, if you look, you know that stars move around the galaxy because they are being accelerated due to the gravity force. And the gravity force, the only way to explain that, if the velocity is not decreasing, it means the gravity force is still basically pretty much the same in the outskirts as in the center. And that means if the distance is increasing, the only way to explain that the force is constant is that if the mass is also increasing. Yes. But when we look at the galaxy, like this one, we see there's a lot of mass here in the center. There's even a supermassive black hole, but outside the galaxy, there's nothing. There are no stars. There's a bit of hydrogen clouds, etc., but there's almost no mass. So if the mass is increasing, is a mass of something that we cannot see. And this mass that we cannot see, this is what astronomers called dark matter. So it's in galaxies, what astronomers concluded is that in galaxies, there is some mass, there is some particles there, which are very massive. There's a lot of mass in there, which extends outside the visible part of the galaxy. Yes. And we cannot see it, so we call it, it's dark. So this would be the graphical impression like for dark matter. So if we have a galaxy in our universe, like the Milky Way, yes, the Milky Way will sit in the center of a so-called of a dark matter halo. So around every galaxy in our universe, or most of them, most of the galaxies in our universe, they will be surrounded by a cloud of particles, which are very massive. They have a lot of mass, but they do not interact with light because we cannot see them, you know, and the way we cannot see them is because they do not emit light, they do not emit electromagnetic radiation. And this dark matter, it needs to be, then we need to have a lot of dark matter. So this dark matter should represent 90% of the total mass in the galaxy. So in the galaxy, most of the matter should come from the dark matter. It should not come from the stars that we see it. And these dark matter halos, they should be really big. And that's the only way, for instance, now you can understand looking at the picture that a star that's in the center of the galaxy or a star which is here at the edge of the galaxy, it feels pretty much the same amount of mass because the mass is everywhere. And that's why a star here at the edge of the galaxies moves around the center of the galaxy as fast as a star which is here in the center. The velocity is pretty much the same because the amount of mass is the same. So that is a possible explanation for why galaxies have these kind of rotation curves. Okay? So what I'm trying to say here is that when we do an astrophysical observation, for instance, of trying to understand why stars move in a galaxy the way they do, so why the velocity of the star is pretty much the same anywhere in a galaxy, whether it's in the outskirts of the galaxy or in the center of the galaxy, we cannot explain that within Newtonian gravity, within general relativity, and take into account the standard model of particle physics, because the standard model of particle physics basically says there are stars in the universe, nothing else. But the stars we can see. So we need something else in our theoretical model in order to explain what we can see, to explain the galaxy rotation curves. And that something else is this dark matter particle, which is there, and it's not part of our physical and mathematical model. Now, we are scientists. And as scientists, we need to ask a question. We need to be very critical about our way of doing science, which is this the only explanation? Isn't there another possible explanation to explain the galaxy rotation curve? So how stars move in the galaxy, how these hydrogen molecules move in galaxies without introducing a dark matter particle into our universe? Well, and the answer for that is no, that's not the only explanation. And the other explanation is the one I'm going to tell you about now. So, as I said, if you do a plot, if you do an observations where you measure the velocity of stars and molecules of hydrogen in our galaxy, what you get is these data points here. Okay? These are the observations. What we expect, taking into account the visible matter that we see, taking into account general relativity or Newtonian gravity, it would be these dashed lines. So it's completely offset from the observational data. Yes. Now, what we said is that, okay, so in order to have strong velocities in the outskirts of the galaxy, we need to increase the gravitational force. And for that, we increase the mass. Okay, so is that the only explanation? Well, this is just one explanation. The other one is that instead of increasing the mass, so that there is saying that there is some dark matter particle out there, we can basically change our gravity law and say that gravity law, the gravity force, does not decrease with 1/r². Yes. And in fact, there was an Israeli physicist called Milgram, who in the 1980s, he proposed a so-called modification to the Newtonian dynamics. So it's a theory of gravity which changes Newton's law of gravity and will also change general relativity. And what Milgram proposed in 1984 is that our laws of gravity, our Newtonian law of gravity, works very well in the center of the galaxy, works very well in our solar system on Earth. So our force of gravity decays as 1/r² in regimes where the density is very high, so like on Earth, solar system, etc. But as we go to astrophysical scales and to the edges of galaxies, then our mathematical equation that describe the gravity interaction, they should change not for 1/r², but to 1/r. So we change the law of gravity. And what is extremely surprising is that with that small change on the gravity law, he was able to explain the galaxy rotation curve. So this is just an example for a galaxy, the NGC 1560, where you have all these data points here. And if we take into account this Mond theory of gravity, so which goes beyond Newtonian gravity and beyond general relativity, we can explain the galaxy rotation curve, the velocity of the stars in the galaxy. While just taking into account the Newtonian force, we cannot explain it. But what is amazing with this theory, it explains much more than just the galaxy rotation curve. It explains many, many other properties of galaxies in our universe. And this just with the standard model of particle physics. So what Milgram proposed that let's not include a new particle in our universe, a new dark matter particle. Let's keep just the particles that we know of. Just let's keep, the protons, the neutrons, the electrons. Let's keep that. And let's just upgrade our general relativity, our theory that describes space and time and the gravity interaction, into something else. And with that, we can explain the galaxy rotation curves and, in fact, other galactic properties. So, as you can see, so this was in 1984. People worked a lot for many, many years on this. And the question for scientists was always, okay, we have this observational phenomena in our universe, but now we have two explanations for that. One is either changing the gravity interaction. Yes, so changing general relativity, basically assuming that the gravity law, the gravity equation that we are using are wrong. And the other one is that introducing a dark matter particle, so changing the standard model of particle physics. So we cannot have that. There can be only one answer for our universe and for the phenomena that happen in our universe. And therefore, people have been working very hard with that. And the answer, not a definitely answer, but a quite strong answer to that question, whether there is a dark matter particle, whether the gravity law is wrong, came in fact in 2006. And this is what basically the last part of my talk is going to be about. So in 2006, there were a group of astronomers in Harvard that they realized there was an interesting phenomena which happened in the universe a few billion years ago, which was the collision of two clusters of galaxies. And they use this event, the collision of two clusters of galaxies, to try to answer the question whether dark matter exists or not, whether there is a particle dark matter, or whether basically general relativity is wrong. So before describing you this phenomenon of the collisions of clusters of galaxies, let me tell you just some basic properties of clusters of galaxies. So clusters of galaxies, as the name says, are made of galaxies. So these are basically the stars, yes, that's what you see. And there is also a lot of intergalactic medium gas. So in the cluster of galaxies is a cluster of galaxies, many, many galaxies together, millions of galaxies together. But in between the galaxies, it's not empty space, there is gas. Now, what is interesting on a cluster of galaxies is only, if you're going to weight a cluster of galaxies, only 10% of the total mass of the cluster is made of stars, is made of galaxies. Most of the mass of a cluster of galaxies is in fact in the intergalactic medium, is in between the galaxies, within this gas. So most of the mass of a cluster is in the gas. So this represents 90% of the total mass of the cluster. Now, of course, when I'm telling you this, I'm assuming that the only mass there is in the universe is the mass coming from the standard particle physics. So it's just electrons and protons, yes? So that's what makes the galaxies and the intergalactic gas. If there is dark matter in our universe, if there is these dark matter particles, then the balance changes completely. And in fact, 90% of the total cluster mass is dark matter, yes? And only 10% is really this intergalactic gas and the galaxies, yeah? So basically dark matter, if it exists, should dominate completely clusters of galaxies. Now, of course, it would be nice to observe a cluster of galaxies and try to measure how many galaxies there are in the cluster, so how many stars. Then we try to measure how much intergalactic gas there is in a cluster, you know, and then try to observe how much dark matter there is in the cluster, and to try to identify if this dark matter exists and if this ratio between 90% of the total mass is dark matter and only 10%, if this is correct or not. So how do we see, first of all, we look at the cluster of galaxies. So this is an image of a cluster of galaxies. So how do we see the galaxies and the gas? Well, the galaxies, we just see it by looking at the light that is emitted from stars. So we can look in the optical range of the electromagnetic spectrum. In the optical range, we can see all the galaxies. So this is what we are seeing here. Yes, all the galaxies. The gas, we cannot see in the optical range. We need to look at the X-ray range. So we need to have telescopes which look at the X-ray. And of course, we'd like to find out a way of seeing dark matter as well. That would be very nice. Yes? But okay, but what is important is that the galaxies you see in the optical, so you just have a telescope which is in the optical spectrum and you see the galaxies. Then if you have another telescope, you can see the X-ray regime, so you can see all the gas that exists in the galaxies. And then for the dark matter, there is a way of observing dark matter in an indirect way. Okay? Oh, and let me again remind you, so 10% of the mass of a cluster should be in the optical, in the galaxies. 90% should be in the X-ray gas. Okay? But of course, yeah, and that's it. Okay? So a way to see dark matter is through a phenomena called gravitational lensing. Okay? So this is not proper seeing in the sense that we see light. It's more like a way of detecting the effects of dark matter. And gravitational lensing is a phenomena that was predicted by Einstein. It's a phenomena that naturally comes within the theory of general relativity. And the reason for that is that the theory of general relativity basically says that if I have some energy and mass in some region of space and time, my space will be curved. So for instance, if I have the sun, which is a very massive object, the space around the sun will be curved. And this leads to a phenomena, which is the bending of light. So light rays, as they pass nearby the sun, they will feel the curvature of space and they will be bended. So one example of one phenomena that happens due to the bending of space is the fact that, for instance, if we are on Earth and we are observing a star, which is on the other side of the sun, for instance, the position of this we will be misled to think that the position of the star is is displaced, will be here, because we have the impression that light travels in straight lines, while in fact light bends. Yes. So this was a phenomena that is comproved and is proven. Yes. So for instance, something that we can see very often, and this is standard astronomy observations, we see, for instance, if we are here on Earth, if we look at the galaxy, which is behind, for instance, a cluster of galaxies, so there's a cluster of galaxies between us, the Earth, and a real galaxy, we will see this galaxy twice. We will see the image of the galaxy in two different positions. Yes. And this is something that astronomers see, you know, and we can really see why this image is the same as this one. And it's not the real image. The position of the galaxy is somewhere else. Okay. So this is a phenomena which is called gravitational lensing. And it's a nice way to use this phenomena to try to probe or to see dark matter. Why is that? The reason is that dark matter, if it is very massive, we have these particles, very massive, they will create huge curvatures in our space and time. Okay? And that means that dark matter, for instance, if we have a cluster of galaxies, like in this image, we have a galaxy cluster with lots of dark matter in here. So we are on Earth, for instance, and there is a telescope looking at a distant galaxy on the other side. The light from these galaxies will be bended. And what is happening is that instead of us seeing a galaxy, you know, a nice, for instance, elliptical galaxy, nicely with a nice shape, we will see that the fact that space-time is bended here, is curved, so will bend light, the image of the galaxy will be completely distorted because there is such a huge curvature because of the dark matter that will distort the image of the galaxy. So this is similar. You can have an analogy if you try to look through, for instance, a straw, an object in the background, through, for instance, a glass of water. What you will see is that the image of the object will be distorted because you see it through a denser medium, because the light rays will bend when they cross water or a different medium. Yes, because they have different velocities. So there's going to be a deflection of the light rays when they touch, for instance, this straw and when they go to your eye. So it's very similar to what happens to a galaxy and the image of a galaxy. The image will be distorted because the lights will go through a different path because it's bended by space. It's bended by the dark matter. Space will be curved, and so this phenomena will happen. Okay, so astronomers have then found a way within general relativity that they can look at galaxies, and if the image of these galaxies are very, very distorted, it means that there must be something very massive in front of us that is causing huge curvatures in space that distorted completely these images. Okay, so that would be a way of seeing dark matter. So we don't really see the dark matter, but dark matter distorts the curvature of space-time, and we can see these effects. Okay? Okay, so now let's go back to 2006 and to what these astronomers in Harvard, what they found out. So these astronomers in Harvard, they found out that there were two clusters in our universe, which a few billion years ago, these clusters, they collided. Okay? And what happened is that, as you know, clusters are made of galaxies and intergalactic medium gas. Okay? And around the galaxies, there should be a lot of dark matter, these dark matter particles, if they exist. Okay? So here I'm just showing you a simulation of the two clusters. So there's a bigger cluster and a smaller cluster. This system is called the bullet cluster. Okay, so you will see that these two clusters will collide. This is what the simulation shows you, that these two clusters will collide. The red bits represent the intergalactic gas, and the blue parts represent the galaxies. So the galaxies, as you'll see, the blue parts, they will just go through each other very quickly. So the galaxies are moving faster than the gas. The gas is getting behind here, and the other galaxies moved really fast there as well. Okay, so this is just a simulation of the two clusters colliding. So what you will see is that the galaxies, they move very fast, and the reason is that in galaxies, they don't interact with each other. There's huge of empty space between them, so they just go through each other. However, the intergalactic medium gas, they will drag behind because there is electromagnetic radiation. There are magnetic fields. So this intergalactic medium gas has lots of interactions. So we'll drag behind in these clusters collision. Okay. Now, what you should remember then is that the galaxies should be these blue parts. Okay. And only 10% of the mass in this system should be in the galaxies, because 90% of the mass should be in the X-ray gas. Okay, so this happens, this bullet cluster collision happened a few billion years ago, and the astronomers, they had the idea of doing a gravitational lensing analysis into the system. Because what they say is that, okay, so if I'm going to analyze, do a gravitational lensing analysis to the system, so if I'm going to see which parts of this system there are more distortions of light, where light bends more, where are the strongest curvature of space-time. In principle, the strongest curvature of space-time should be where there is more mass, because more mass is more energy, so space and time should be distorted more. So the strongest lensing phenomena should happen in where there is the X-ray gas, because that represents 90% of the mass of the cluster. While in the galaxies, which only represents 10% of the mass of the cluster, there should be only a little bit of gravitational lensing. So there should be some lensing, but the images should not be very much distorted. So this will be a nice example to do this kind of analysis and to verify if it's true that where most of the mass of a galaxy cluster lies here in the X-ray gas. So what they did is that they took two pictures, one with the Hubble Space Telescope. This is here, this picture here on the right-hand side, where in the optical regime, they took a picture of the Hubble telescope. So you have one cluster of galaxies here, another cluster of galaxies there. And they went to use this Chandra telescope, which is an X-ray telescope, which basically took the picture for the same region of the sky. Here it is, where the Chandra telescope in an X-ray region, so it only sees basically where is this intergalactic medium gas, so this X-ray gas. And you can see it, it's in here. Yeah. So these astronomers, they overlap the two images together. So this is what I'm showing you here. So this is an overlap of the two images. So it's the optical picture on top of the X-ray picture. So here you can see the X-ray. So here you can see where most of the intergalactic medium gas is. So it's basically in here. And the galaxies are basically what is painted here in blue. So this is lots of galaxies, as you can see here. Here there are not so many galaxies. And here there's also lots of galaxies there. Okay. And with these pictures now, they went to do the analysis to see where are the strongest now gravitational lensing phenomena. So which parts of this system there is a stronger distortion of the images from the background galaxies. So where are the strongest gravitational fields in this system? Okay. So when they do that, this is what they find. So again, I'm splitting the images from the Hubble Space Telescope. So here are the galaxies here. The galaxies are there. And this is the X-ray gas. These two, the yellow-red areas here. Okay, it's from the Chandra telescope. Okay. Now, the green lines represent the places where space-time curves more. So these are the places where lensing phenomena is stronger. So there's lots of distortion of background galaxy images. Yes. And the strongest gravitational lensing goes here and goes there. So that's where the strongest gravitational lensing here, really on top of the galaxy. So you can see here, the strongest gravitational lensing happens within these curves here, and the other one happens there. So as you can see, the strong gravitational lensing, they sit on top of the galaxies. So the curvature of space-time is stronger where the galaxies are. This curvature of space, this bending of light, is not very strong where the X-ray gas is. And that means, if you remember, the X-ray gas should in principle represent 90% of the total mass of the cluster. But that's not what the observations are telling us. The observation telling us that most of the mass of the cluster is in fact in the galaxies. It's not on the X-ray gas. So that means that on the galaxies, around the galaxies, there should be something there. There should be something very, very massive around the galaxies. And this thing, which is very, very massive around the galaxies, we cannot see, nor in the optical, nor in the X-rays, nor in any other wavelength. And so this is what the article is called, what would be an empirical proof for the existence of dark matter. So it seems that there is indeed some dark matter particle in our universe, which creates these halos, these spheres around galaxies. So it's not around the X-ray gas, it's around galaxies, okay? And creates these strong gravitational fields. And this is somehow proven by this observation. So dark matter, so the general consensus in the community is that dark matter is probably an undiscovered particle which goes beyond the standard model of particle physics. It has to be something very massive and should not interact with the electromagnetic field. So we should not be visible. Okay. So hopefully we'll be able to detect this dark matter particle in particle physics accelerators in a direct way. Okay. For instance, within the Large Hadron Collider. Okay. That's what I wanted to tell you about today. Thank you very much for your attention.
Thanks, Doctor. Thanks. Well, I'm talking about myself now. I'm mesmerized by your talk. It was incredible, well explained, reachable, accessible, and the concepts well managed really, really good. I think that most of the people that is here with us is also feeling the same. So now, please, if you want to make questions or any observations about what we have seen right now, you can write it down on the chat, or you can open your mic and video and talk directly to the Professor David Mota. I hope some of you have any questions. If not, I have one. And I would like to ask you, sir, if there is a person or a professor or any kind of personal inspiration that you receive at your age that make you decide to do what you do today for a living, that is do science in astronomy and astrophysics.
Yes, there was. So I did my undergrad. In fact, when I started my undergrad, I did my undergrad in engineering. So nothing to do with astronomy or more theoretical physics or mathematics. But I had a professor at university in my last year who was someone who was interested in cosmology. And it was the person who gave a course, in fact, in cosmology in my undergraduate. And he basically motivated me to work in cosmology because he was the first one to talk to me about the problem of dark energy, which is another problem. I would be happy to talk here about dark energy as well. It's a different problem in physics and in cosmology. And that was the problem that interested me and basically led me to apply to do a master degree in the field of cosmology and then to do my PhD, etc., and to follow this field. Yes, but was someone, in fact, already at university and make me change for engineering. So I was doing engineering, and I changed my path completely in there.
Okay, thanks. Well, there is a person. There is a question in the chat. You can read it by yourself if you want, or you prefer me to read it.
No, I think I can read it. I think the question that I see is that how exactly is the gas of the collision between the two galaxies interacting in an electromagnetic fashion?
What a good question.
Yes, yeah, precisely. So it's basically an electromagnetic interaction, and also yeah, because there are magnetic fields, and there are in our galaxies. So basically, the interaction is electromagnetic. Yes, you are right. Yeah, in there. Yeah, and while that's not the galaxies. So that's the intergalactic medium gas. Yes. The galaxies, they just go through each other because they are, I would say, let's think about them as neutral objects. They do not have charge in galaxy. So the only interaction they feel is just gravity. So they just go through each other. While the gas, since you have these magnetic fields, etc., as they cross the gas, they will start interact in there. Yeah, and so they will drag behind. Yeah. Okay, so I hope that was clear.
Yes,
the other question is, okay, very good, thank you. So the other question is, what kind of experiment could prove Mond right or wrong? So,
great question.
Yeah, yes, it's well, right. Okay, so at this stage, what I would say is that it's extremely difficult to prove a theory completely wrong. Well, the only way is that, so Mond in itself is the one that I presented to you is a non-relativistic theory of gravity. So general relativity is a relativistic theory of gravity. So it takes into account, goes beyond the Newtonian theory of gravity. While nowadays there's no viable theory, a relativistic theory of gravity, which has in some regime a Mond regime. Okay, sorry. I want to put this in a simple terms. Okay. So the bullet cluster observation, the one that I showed you, is something that cannot be explained, or at least there's no article published that can explain the bullet cluster observation, the one that I showed you about, the collision of clusters, within a Mond theory of gravity. So up to now, this would be an observation that rules out all the theories of gravity which are not general relativity or that do not have a dark matter particle. After saying that, this is a very strong statement, yes? So after saying that, there are people working on theories of gravity, like Mond, which are trying to explain the bullet cluster phenomena. And up to now, people have been developing the mathematical formalism. They are already computing some astrophysical observables. They can explain the galaxy rotation curves very well. They can explain several other phenomena which we would need dark matter, so they can explain all these other phenomena without dark matter, but nobody has ever showed with a proper simulation the bullet cluster and how to explain the bullet cluster observations without a dark matter model. So people are working on it, but nobody has still given proper proof that Mond could explain the bullet cluster observation. So at the moment, that's why I think most of the community is more on the opinion that there is a dark matter particle. But that might change, yes? That might change. So the other question, is that true that Newton's gravitational constant is the constant with the least precision obtained among us? If so, why? It's true that the measurement of the gravitational constant, the Newtonian one, is quite difficult. but also depends where you do the measurement of this gravitational constant, because one thing is to measure, for instance, the value of the electromagnetic gravitational coupling constant, for instance, the fine structure constant, or on Earth, and to do the same measurement of that constant of nature in another galaxy. So it's very difficult to compare where do you measure these constants of nature. So Newtonian gravity, the Newton gravitational constant, and tests on general relativity are very, very precise, in fact, within the solar system. Not the measurement of G itself, but other tests of general relativity. So in the solar system, the precision is up to 1 in 10,000. So it's not the best precision, but it's really well done, well measured. The problem is that what is happening with gravity at galactic scales or clusters of galaxy scales, and what happens to the laws of physics in other astronomical scales, and that's the question that people are asking. It's very different to test a theory on a laboratory, on Earth, on the solar system, and testing that same theory outside. That's why, for instance, the merger of black holes and the observation of gravitational waves is really important, because we are testing general relativity, not in our solar system, but billions of years, light years away from us in other systems in the universe. And this is something that you have to keep testing and testing and testing until you see something strange. Yes. The other question, could we say that all we know about the universe is an illusion due to the effects of dark matter? I wouldn't call it an illusion. So if dark matter exists and it's a particle that basically it very weakly interacts with light, so we don't see it, so it means it's there. You know, it's like the orbit of Uranus. You know, the orbit of Uranus was not agreeing with what we would know about Newton's gravity, and that was because we did not detected Neptune in the 19th century. After we have detected Neptune, you know, we understood the orbit of Uranus. Even if Neptune was a dark planet, you know, if we knew it was there just by some other method besides looking at it, I think as long as things are self-consistent, it's fine. So I don't think you can call it an illusion. I think the word illusion is a bit too strong to say that, you know. So if Mond is an accurate model of reality, would it affect our prediction regarding the expansion of the universe? If so, how would Doppler redshift still be what we observe? Okay. So there are two types of Monds. There was the classical Mond that was invented by Milgrom in 1986, 1987. And that Mond could not explain the expansion of the universe. Just like it was a kind of Newtonian theory of gravity cannot explain the expansion of the universe. Later, people have developed better theories of Mond, okay? So they have a different name, okay, but let's call it Mond. And they explain quite well the large-scale behavior of the universe, the expansion of the universe, the Doppler redshift, etc. So it can be well explained, because these theories of Mond at very, very large scales of the universe, they are just like general relativity. So they do not differ from general relativity at the largest scales of our universe. These theories of Mond, they differ from general relativity at galaxy scales and clusters of galaxy scales. That's where they differ. So the very large scales, all the phenomena related to the expansion of the universe, redshifts, etc., is pretty much the same. So you can think like it's just like general relativity is just Newtonian physics on Earth. Yes, it's when we go outside the Earth, as we go to the solar system or to even outside to galaxies and clusters of galaxies, that's when general relativity starts to become different from Newtonian gravity. Mond is kind of the opposite. Mond agrees with general relativity at very large scales. And as we go to cluster of galaxies and to galaxy scales, that's where Mond starts to disagree with general relativity. Yes. So the global properties of the universe, those Mond can explain quite well as well. Yeah. Well, it depends on your theory of Mond, but yeah, I think there's no point going to details now.
Okay, I see that there are no more questions in the chat. I want to have a couple of questions yet. And one of the question is, what is the part of your job that you enjoy most about teaching astronomy and astrophysics at the University of Oslo?
Yeah, so I think I like a lot of my job is the balance between being able to do research. That means being at the forefront of the knowledge that physicists have about our universe. You know, it's always exciting to discover a new phenomena that we do not understand, you know, within our theoretical models, or to read about someone who proposed a new theory, for instance, of gravity, which can explain the phenomena and goes beyond Einstein general relativity. It's always very exciting to have this kind of following this kind of developments in the physics, in the scientific community. But on the other hand, to try to explain these new discoveries, both in terms of astronomy, so both in terms of observations, as well on the theory side, to students, both at, you know, I give course at the PhD level or the master level, but even at the bachelor level, even in the outreach level, because I think it's really important to have this balance and to tell people about what's going on in terms of what do the scientists and astronomers know about our universe, because I think everybody's interested, even our mothers and grandmothers. They would be excited to know, you know, like what kind of phenomena goes on in our universe, you know. And I think what I like most is this balance, this kind of trying to teach what is the most updated information that we get from observations and from theories about our universe. Yeah.
Okay, thanks. There is another question in the chat.
Yes. So what measurable properties should a dark matter particle possess, besides, of course, the absence of electromagnetic interaction? What would be its spin? Okay. Would it be a boson or fermion? Where would it fit in the standard model, if it fits at all? Okay, that's a very good question. It's a bit complicated as well. So it depends on the level. So there are many candidates for what dark matter can be. So just very quickly, so one of the first candidates that people thought about is that dark matter would be just, for instance, dwarf stars or dwarf galaxies that we can't really see, because they are made on the standard model of particle physics, so they are made of electrons and protons, etc. But they are just these kind of dark objects, or planet-like Jupiter kind of planets, you know, that there are a lot in our universe that we wouldn't see. So people put out this kind of possibility. Even primordial black holes would be a candidate for dark matter. So people put out these hypotheses and try to do measurements, and astronomers find out that it's not possible to explain all the different phenomena in our universe just with this kind of standard model dark matter. So we have to go beyond the standard model of particle physics, and for that we need to include new particles. So besides the electromagnetic interaction, which needs to be very, very weak, otherwise we would see it, they need to be very massive. That's the other biggest property. And I think these two are the key properties. Now, is this particle a boson or a fermion? That depends. We have nowadays dark matter candidates which are fermions, and we have dark matter candidates that are bosons. They have different properties, and they can be distinguishable in principle. Because they have signatures, they have effects on the structures, on structure formation, the formation of cluster of galaxies, the formation of galaxies, the inner cores of the galaxies, etc. That will be different if it is a boson or if it is a fermion. So if there's a different spin, an integer spin or not. Nowadays, people don't know which model is the best one, whether dark matter is a fermion or a boson, or it's something else. We are basically testing many models. For instance, with particle physics accelerators like the Large Hadron Collider, we tried, for instance, to detect supersymmetry, in supersymmetric particles. So supersymmetric particles, they would be dark matter candidates. And up to now, the supersymmetry perimeter space is reducing and reducing its perimeter space. So there are many dark matter models which are ruled out already from particle physics experiments. Also, from the observational point of view, people are trying to detect dark matter via indirect methods, via direct methods. And that also, since we haven't detected any dark matter particle, that also kills many different models. But in general, there are still candidates of dark matter, viable candidates for dark matter, which are both bosons and fermions. So this is not, there's not definitely answer for that. So I think the only thing that we need for dark matter is that it needs to be heavy and weakly interacting. Yeah, that's the only two main properties that we need. Skill of computational programming. Yes, it is very important. I think computing and learning how to code and learn how to analyze big data sets, it's extremely important in astronomy. Either for when you do observations, you collect so much information that you need to know how to treat that information. You need to know how to analyze that information. And for that, you need to basically nowadays, you can't use naked eye, you really have to use software and code programs which can do the analysis of the data for you. Also, for instance, if you want to compare, you have a given theoretical model, like one of these Mond theories, and you want to see if it can explain the bullet cluster collision, you need to simulate that. So you need to solve all these differential equations that usually are part of the mathematical and the physical model. And that usually takes a lot of computational methods, algorithms. You have to run in supercomputers. So it can take months running a single program in cores of 10,000 computers, laptop. If you put 10,000 laptops together and you put your code to run, it would take like weeks or months to run. So it's huge simulation, and you need to know basically how to do this computational programming. So I think computational program is, unless you do pure theory, pure theory, so you're just concerned about theoretical models, and you don't really care about the observational side, that you might not need so much computational programming. But in astronomy, definitely one of the pillars for astronomy is to know physics, and it's to know computing. That's for sure. Yeah.
What do you think about the application of artificial intelligence on the evaluation of models and the proposal of models about understanding the nature of the universe, regarding how efficient artificial intelligence have been proved to be in other areas? Do you think that artificial intelligence could help us through physics and mathematics to learn approaches or realities of the universe that are incapable for us to reach?
Yeah, that's a very good question. I think the answer is yes. Artificial intelligence can help us, like doing things like machine learning, etc., on the analyzing the data. We need that, in fact. So there are the two issues. One is that yes, it can help us maybe to extract information from the data that we humans cannot extract by ourselves, because artificial intelligence, these machine learning algorithms, they look for patterns in the data that maybe we human beings do not can see them, these patterns. On the other hand, I think maybe even more important is that artificial intelligence algorithms will help us basically to tell us which kind of data it's really relevant for the research we are doing. Like nowadays experiments, they collect so much data that, in fact, for instance, in CERN, for instance, in future experiment like the square kilometer array, the SKA, they will collect so much data that, you know, basically we throw away 90% of the data that we collect. So we do an observation, we get all this data into our computers, and we have to erase 90% of the data because we don't have space to store it. So these 10% of the data that we will store in our computers, we need to know which data to store, which one is the good data. And we can't do that humanly. We have to do these kind of decisions on the minute, on the fly. And that we need to set up artificial intelligence codes to basically to make that choice for us, to choose for us which data we should keep it and which data we should not keep it. Now, this is extremely dangerous because we are the ones teaching these algorithms what data should be interesting. But when we tell the artificial intelligence algorithm, hey, this is interesting, this is what you should keep, and the rest you throw it away, maybe you are throwing away data, which is extremely important. It's data that you would not understand, you cannot explain. So data that will rule out, for instance, general relativity, data that might rule out a dark matter particle, because, you know, we don't know. So it's a knife of two sides, you know, it's a catch-22 kind of situation. We want the artificial intelligence algorithm to help you to select the data, to look for patterns, but on the other hand, we may run into the risk of throwing away very valuable information that, you know, they might give us some hints about the universe and the laws of physics, and you just think that is rubbish data and you throw it away, and you are throwing away very important data. So it's a field that people need to be very careful when they use artificial intelligence. Yeah. So it's one needs to be very careful, useful, but very careful with that.
Okay, thank you, Professor. There is another question, and in fact, it's related to what you have been talking about recently. Will it be a fallacy to say that if dark matter is 90% of the universe, then we only know 10% of the nature of the universe? You can read it in the chat in case you didn't understand properly what I said.
Yeah, well, in fact, unfortunately, I think it's even worse than that. We only know 4% of our universe. So if we take nowadays, a measure of the whole matter and energy there is in the universe, about 20% is dark matter of the whole universe. There is around 75% of something that we call dark energy that I haven't talked about here. So the universe is dominated in 75% of the total matter energy content of the universe is this dark energy. And what we are made of, the whole standard model particle physics, you know, what you see in your daily life, what you will see since you were born until you die, you know, the stars, the laptop, people, everything, galaxies, everything that you see around you, which is basically a quark up, a quark down, and an electron, you know, that only represents 4% of our universe. So it's huge, the amount of ignorance that we human beings, we have with respect to our universe. So there's a lot of work to be done. There's a lot of research and to be done in terms of our universe and the laws of physics. It's really, it's only 4% of our universe that we can really describe in a proper mathematical and physical way. The rest of it, we know it's there, we know dark matter is there, we know that dark energy is there, but we cannot really explain it yet. You know.
Okay, I have one more question. As we have seen in this talk, you are really good doing outreach research. What do you think is the importance of the outreach activity of astronomy and science in today's society for a social appropriation of the science and the people?
Yeah, it is. For me, I believe it's extremely important, the outreach side. I think when scientists just live in their own world with and have this knowledge about the universe and the laws of physics, etc., and they don't pass it on to people who are not scientists, who do some other jobs in the society, I believe that's really a pity, because I think most of the people, they are interested to know what's going on in our universe. Most of the people are interested to know where we are coming from, how the universe is evolving, what is a galaxy, cluster of galaxies, etc. And moreover, I think outreach allows people also to learn about how science develops, how scientific knowledge is built up, and also I think, especially for the youngest generation, it's a way of attracting, the younger generations to learn about physics, to learn about mathematics, to learn about computer science, as was mentioned in the questions, to learn about this kind of, I would call them more hardcore scientific knowledge, which are extremely important to develop society, especially countries that need a boost in terms of development. I think the astronomy and outreach in this kind of in this kind of fields of research will be a way of motivating people to come in to study physics and mathematics or engineering and computer science. And these are the tools that in the future a society and a country uses to develop. So outreach leads not only to satisfy the curiosity of people, but I think has a very practical influence and a practical effect on countries and on people and on societies. So I think it's really extremely important. Of course, it's not always easy to do outreach, because sometimes the scientific questions are so complicated, the mathematics and the physics is so complex that usually one needs to a certain basic scientific knowledge. Like I think in this audience, I think most of the people, they have basic knowledge in physics and mathematics. So for me, it was easy to transmit some of my knowledge to you. But if I would go down to maybe a high school level, or even to primary school level, I think it's extremely important. But it gets more difficult and difficult. But I think maybe governments should support this kind of activities more, or even within the universities, they should be more supportive of people doing outreach, even to primary schools and to secondary schools. Yes, I would say so.
We agree. There are two more questions, and sorry, because we want to take advantage as much as possible at the level of person that we have in you today. So the next question reads as follows: can a simulation recreate the whole universe, or an approximation of it?
Yeah, well, so there are some simulations, numerical simulations, which recreate the whole visible universe. These are computer simulations. They are huge. They take a long time to run. But so the question is, well, the short answer is no. There's no numerical simulation that can recreate the whole universe, from the smallest scales of planets all the way to gigaparsec scales of the whole universe. There's no numerical simulation that can do that. It's impossible, numerically impossible, because it would take more than the age of the universe to compute and to solve the equations from the smallest scales of planets all the way to the largest scales of the visible universe. However, what people do, they simulate, for instance, just a galaxy. And there are people who simulate the Milky Way very well. So they can simulate a Milky Way, they create the disk, they create the spiral arms, the amount of stars in the Milky Way, and you get the properties of the Milky Way very nicely. You get all the velocity of the different stars, the temperature of the gas, so they can do that. So this is one kind of simulation. Another kind of simulation, people simulate more, for instance, one cluster of galaxies. So they focus on scales of about 1 megaparsec, so maybe 1 million galaxies together. And again, they can simulate the intergalactic medium gas. Well, there are some people who even simulate the bullet cluster, collision of galaxies, etc. And then there are other kinds of people. This is more what I do, in fact. We try to simulate the whole universe, but then in our simulations, we only have the very large scale structures of the universe. So we can see filaments, we can see superclusters of galaxies, we can see big voids, regions of the universe where there's nothing. But in our simulations, we cannot see individual galaxies, for instance. We do not see individual stars nor planets. So all the simulations that we have in our universe are very large scales or intermediate scales or very, very small scales. It's impossible to do a whole simulation of the whole universe. Yes. Yeah.
Thanks, Professor. There is another question. This one is made by Marian. Sorry for the other people that I haven't mentioned their name and the question. This one comes from Marian. She said, what is the, do dark matter have an electrical charge? Could it be a conductor?
Yeah, good question. So dark matter, so people have investigated different types of dark matter particles. Some of them charge dark matter particles. Usually, if it has an electrical charge, that would mean that it would interact with the electromagnetic field. And we know from observations that this interaction with the electromagnetic field needs to be very, very weak. So weak that we don't see it, yes, basically. So usually what people give, they don't give an electrical charge to the dark matter, but they give some other kind of charge. So just to give you an example, so quarks, they have electrical charges, but they also have another kind of charge, which is the strong interaction charge. That's called color. So, and the strong interaction charge has three types of charge. It's the three colors, blue, red, and green. The electromagnetic charge has only one type. Well, there are two types of charges, the positive charge and the negative charge. So dark matter, it might have some kind of charge. It's not the electromagnetic one. People, yeah, there are very strong constraints on being electromagnetic charge. So it's not the charge that you're thinking about it. So if dark matter has a different kind of charge, then it can be a conductor for that charge, but not for the electric one, okay? So if you're thinking about electrical charge, then the answer would be most probably not. Dark matter does not have an electrical charge, so it won't be a conductor. But it can be it can have a different charge, and that will be the conductor of that other charge. Yes.
Okay, very technical the question and very accessible the answer. Thank you. I have another question from Fabio Pimentel. He's asking, what is the programming language that you mostly commonly use in your researches? Oof. Yeah.
So that depends a lot of what kind of research you do. So for instance, the kind of simulations that I do, that we try to simulate very large scale structures of the universe using, for instance, dark energy or dark matter models, we use, usually programming language is going to be C++. Okay. Now, when people, so this is going to be to solve differential equations. So people who analyze data from telescopes, they usually would use, well, depending on what kind of telescope, they use Python. Python is a very common language that people use a lot in nowadays astronomy. There are some people who still use some other kinds of language, like in more software kind of language, like IDL, to analyze, for instance, images. So for instance, people in solar physics, they have solar telescopes. I know they use a lot for image treatment of the sun's surface, etc. They use IDL. But I would say probably the most used language nowadays is Python within astronomy to do data analysis. And for people who do solving numerical differential equations, doing more theoretical work, it's going to be C++, I would say. Those would be the most using. But Python, I would say, it's a great language for any young person to learn. Yeah.
Okay, it looks like there are, there's an image. Okay, it looks like there is no more questions, but we have a very important last one, sir. What are the best books that you recommend for physics students that would like to learn about dark matter? Or in
that's so So there was a question about gravitation in general, yes, and then so for well, there are a few. So to learn about general,
take your time because they will write down all the titles you say. So take your time and give out the books you recommend because they wanted to be accessible for that material for them to learn more about what you have shown us today. There's no pressure, but take your time.
Okay, well, maybe I should, the best would be that I send you an email with a list of the books, and then maybe you can share with the people. I think that would be the best.
Okay,
I'll tell you
that. I could do that, and I will do that if you send me the list, but say 3 books now.
Yeah. So one of them that I really like, it's a massive book. We call it the Bible in gravitation. It's a book called Gravitation by Kip Thorne, John Wheeler, and it's a huge book, but it basically, no, Kip Thorne is the Nobel Prize now. Yeah, so it's a huge book where I think if you have a question about gravity and applications of gravity, especially within general relativity, that's the book which has, I think, everything. It's a huge book, has all the references. It's extremely technical. So so I think usually you should not aim to learn general relativity and gravity from that book. I would say that a very nice book, an introduction book to general relativity that I like very much is a book by Bernard Schutz. It's called An Introduction to General Relativity. It's extremely well written. The level of mathematics is quite good. You don't need to have a very high level of mathematics because general relativity can be taught in different levels of mathematics. So Bernard Schutz, I think, is a level that any student in physics who is in the bachelor degree of physics can learn it and just read it and understand general relativity. Yeah. Now, if you want to go beyond general relativity, if you want to study theories which go beyond general relativity, then there's then there are not many books. In fact, what we have is the so-called review articles on the field. So these are articles that you can download for free from the web, in particular from the archives. That's a huge database of, I would say, 99% of scientific articles written in astronomy and in cosmology and high energy physics. They are there for free for anyone in the world to download and to read. And these books or these review articles, they are there as well. And there's one which is called Dark Energy, for those who want to study it, by Luca Mendola and Shinji Fujikawa. Again, I can send you, I think the best is that I send you the email, yes, with that. And there's another one which is Beyond the Standard Cosmological Model. So it's all the theories that go beyond general relativity and the standard model of particle physics. Everything more applied to, so all these books are very theoretical, yes, so they are not astronomy oriented, because you asked me about gravity. Gravity is something that is more about calculations and yeah, it's more that. Yeah, but I can send you an email. So just send me an email to me just to remind me to be sure that I send it, and I can send you a list of the books. Yes.
Okay. So I will send you that email as sure as this conference ends. As soon as so, as my position of National Outreach Coordinator for Astronomy Union in my country, Dominican Republic, and member of Dominican Astronomical Society, Astrodom, we really thank you for this extremely good conference you have given to us. This will be very helpful for us to do outreach activities about dark matter and gravitational to students on schools and our academical institutions. It's a pleasure to us, as I've said before, Mr. Dr. David, this event in collaboration with you. And as I have said before, this will be the first one of many to come. We really enjoyed the way you explain so technical subjects. And we will be communicating with you through email to do the coordination. Maybe we could have you in Dominican Republic in the future, next year. So let's thank you. If any one of you could want to say something to the professor, this is the moment, or you should shut up forever.
No, it was also a real pleasure for me, and I would be happy to come back and to maybe next time I can talk about dark energy. So another mystery.
Okay, now you have picked yourself, but the new subject of your new conference will be dark energy. Will be discussed today, so emails in the, very soon. Then nada más que decir, señores, muchas gracias a los que pudieron asistir, y vienen más eventos como este en colaboración. El año que viene va a ser muy bueno. Vienen cosas buenas y la vamos a hacer posible en colaboración. Muchas gracias. Thank you, Mr. David. Gracias, presidente. Gracias a todos los miembros de Sociedad Astronómica Dominicana y la comunidad de estudiantes de física que han asistido. Más adelante, esta charla será subida a los canales de YouTube para que el público tenga acceso a esta importante información y a este material. Thank you very much.
It was a pleasure. Okay, take care, everybody. Hope to see you soon. Yeah, thank you. Bye-bye.